Welcome to lecture series on the course Calculus of One Variable. In this lecture, we will discuss the notion of subsequence. So, having understood the notion or the concept and the properties of sequence, we now are ready to discuss another subtopics of this particular chapter, that is subsequence. Now, subsequence is the term that is generated from the given sequence or from the sequence. Given any sequence, uh, when do we say that a part of it is a subsequence of that given sequence? Okay, so just like the terminology that we have in a set theory, a subset of a set, we have over here a subsequence of a given sequence. So let me start by giving a rough idea of a subsequence in a sequence. So if we have a sequence, say xn, basically sequence is a function which is which is from set of natural number to a real number, right? And we denote it in this way: x1, x2, each terms, okay, x3, and this goes on. So this is the notation we used: x1 comma x2, x3 comma x4, x5, x6, x7, x8, x9, and this goes on, right? Now this is the given original sequence whose domain is a set of a natural number. Now if I restrict, say, some infinite subset of this natural number as a domain to this function, then we may skip certain terms from this without changing the order of the terms of the sequence. Okay, say for example, if I take s to be equal to, say, 1, 2, 5, 9, 12, 14, and this goes on. Now corresponding to this natural number from this sequence, we have the term x1, x2, x5, x9, x12, x14, and this goes on based on this defining set S that we have. Okay, so this is one rough example I'm giving you, and you can see that the terms in this sequence are exactly the terms in the given sequence, except for some finite terms, except for some terms, except certain terms of this sequences are this sequence is missing, right? Like for example, I have not taken x3, x4, and then I've directly gone to x5. Then again from x6 to x8, some terms x8, some terms are missing. The reason is that I'm restricting this function on this set S. Instead of making it to go from set of natural number to set of natural number, I'm restricting it to the set of this S to R. Okay, now we can generalize this. You can take set S as anything, and you can derive as many subsequence as you want. So because the set of natural number is infinite, and so you will have infinite choice of a subset of a natural number. Okay, choice of an infinite subset of a natural number, right? So this is just one example. Mathematically, we just write it as a restriction of x to an infinite subset of a natural number. Okay, so let's write down formal definition for this, and then a couple of examples. Definition of subsequences. So let x from n to r be a sequence. Then a subsequence is the restriction Now, this is again a mathematical term. Understanding the concept of function, one can very well define this restriction of a function. So, restriction of x to an infinite subset S of n. So, basically, instead of domain n, you will have S of, yeah, instead of n, you can have any subset S over here as a domain of this given function. Okay, so let's try. By the way, we x of 1, x of 2, we call as simply x suffix 1, x suffix 2, and this goes on. This is the terminology we are used to, and we have seen in the terminology of sequence. So if your set S is a set of even natural number, then the subsequence that you will get corresponding to each element of this S. So it's a, then the subsequence is, so you first, you even natural number is 2, so the first term is x2, x3, sorry, not x3, x4, then x6, then x8, and this goes on, because here S is nothing but it's a set containing two element, a natural number 2, 4, 6, 8, and this goes on. So corresponding to each natural number, I mean each even natural number lying over here, we have an sequence that is formed. Okay, so this is your first element in the sequence now. This is the second element in the sequence which you have generated. S6 is actually the third element in the new sequence which we have generated. And this is the subsequence of the sequence X. I assume that the sequence given over here is X itself. So X1, X2, X3, X4, X5, these are the terms of the sequence, and I have taken only these terms. Okay, so this is the new sequence which we have got. One thing you may note down that we are not disturbing the order of the sequence. We cannot write x4 first and then x2. This is not a set. This is the order n tuples. So x2 first, then x4, then x6 and x8, and it goes on. Okay. And also in the definition, this term is very important in finite, because if we take finite, then corresponding to that we will get only finite values of xn which we are not in search of. Second example, if I restrict instead of even, if I take S1 is a set of, okay, simply S, if S is a set of prime numbers, then the subsequence that we generate from this S is x1, sorry, x2, because 1 is not a prime number, x3, x5, x11, and this goes on. Okay, so this is the new sequence that is generated from the given sequence, and it's called as the subsequence of the given sequence. Okay, so how we can formulate it, or how we can put it in a simple notation, using the given notation of the sequence. Okay, before that, there are certain axioms which I'll be mentioning. The first one is called as well ordering principle. Well ordering principle. So this principle is a very basic principle which uh, which talks about the least element, the existence of least element in any non-empty subset of a natural number. Okay, so if we have a subset of a natural number which is non-empty, then it is it has a least element. So this observation is very clear to everyone, and so this is considered as an axiom or the principle. Basically, what we mean by a least element, it's a lower bound which is contained in the set itself. Okay. Now we know that the set of natural number itself has a least element, right? So if I consider any subset of a natural number, it's definitely going to have a lower bound, but unless and until we know the set, we won't be able to spot the least element of that particular set. But it is very clear from this principle that there will always be a least element for that set. Okay, so that is, there exists an element or lower bound which belong to the set itself, such that that element acts as the lower bound. Okay. Now the consequences of this well ordering principle is that any infinite set of a natural subset of a natural number, the element in it can be arranged in a ascending order, right? So you first take the least element, then you take the element which is greater than this element, but the least when you remove the first element, and then again you remove this two element from the given set and you take the least element, so that element might be greater than this two element. So in this way you can arrange the member of this infinite set of a natural number in a in an order, in an ascending order. Okay. So ascending in the sense, you first take the least element, then you take the element which is greater than the least element, then again you take the element which is greater than the least element but the least among the remaining element, and you proceed further. Okay. So we consider it as a proposition, we take it as a proposition. The proof is very simple. In fact, the consequences of this well ordering principle, which I would leave it as an exercise. So an infinite subset S of n can be listed, that is, the element of this set can be listed as, okay, so this is the way. The first element I will call as n1, that's the least among the element, then n2, then you have n3, and this goes on. Say at some point you have nk plus 1, and this process goes on. It never ends as the set is infinite. Okay, so this n1, n2, n3 till nk plus 1, and it goes on, are the element, are some natural numbers and the element of s. And since we know that from this set we can find the least element, we can list them in this way. Okay. So if n1 comma n2 comma n3 and this goes on, is the member of the set s. Okay. How do we know that n1 is the least element? Definitely the set is going to have a least element. I will call it as n1 because of the well ordering principle. Okay. So since it's an infinite set, it will have at least one element. So the set is non-empty and it's a subset of a natural number, and therefore by well ordering principle it's going to have a least element. I call it as n1. Now you take the set S and remove n1 from there. So you just consider S difference n1. But removing a finite element or one element from an infinite set won't make it finite. It will still remain infinite, and therefore the given set will be again infinite subset of a natural number, and so it's going to have a least element by well ordering principle, and we call that the second least element as n2. And in this way, so therefore the relation between n2 and every other element of S will be n2 is less than or equal to every other element of S except for n1. Okay, since n1 is the least element of S, n1 has to be less than n2, and this goes on. Okay, so because of this, we can arrange the element of subsequence, using this idea. So we have that as we write down it as a node. So in the view of this proposition, above proposition, the subsequence can be denoted by x and k, okay, where n1. So here k is varying. So this subsequence is generated by restricting the given sequence to S, where the element of S can be listed in this way: n1 less than n2 less than n3, and this goes on. Okay, so where n1 is less than n2 less than nk, and this goes on till, sorry, n3, this goes on till less than nk, some general k, nk plus 1, and this goes on as the set S for which the sequence is restricted is infinite. Okay, now I would like to go back to this example. This example. So in this case, if I write down this using the notation which I've mentioned just now, then this x2 become xn1, x3 x4 become xn2, x3 become x6 become xn3, and this goes on. Okay, so how do I relate this nk to k? Okay, k is actually the placement of the new sequence. So when I say xn1, it's the first element of the subsequence. Xn2 is the second element of the sequence. Xn3 is the third element of the given subsequence, n3. Okay, and it goes on. This k is moving from 1 onwards. Okay, so now in this case, just look at this. N1 is equal to 2. Okay, and your k is equal to 1. So just relate this n1 with 1. Then again you will see this n2. This is the second position of the subsequence. But you take it from the fourth element, fourth term of the sequence. So that k denotes the original placement of that term in the given sequence. Okay, so you will see that n2 in this case is equal to 4. Okay, and this goes on. So in fact, in general, you can relate this nk to k, and if you look at this, both this example, you will see that nk is always greater than or equal to k. It can be equal to k if I start the sequence from subsequence from x1. Say this is the subsequence. In this case, you just compare nk with k or n1 with 1. N1 will also be equal to 1, and 1 is also equal. So it might be equal, but nk will always exceed k for every k. Okay, so this observation you can observe through the various example which we have produced here so far. Okay, so therefore nk will always be greater than or equal to k in the sequence x and k, if you compare it to the given sequence. So that is one of very important observations which one have to make, so that uh, defining the properties, so that we might be using this while defining the properties of the subsequence. So I call this as an observation, nk is always greater than or equal to k for every k in x and k, right? Okay, so once we make these observations, we are ready to define a convergent of a subsequence the way we have defined a convergent of a sequence. Now, the very first question that should come in your mind: if the sequence is convergent, does the subsequence generated from that sequence, is it convergent? Okay, or if say one subsequence of the given sequence is convergent, is the original sequence has to be convergent. So before that, let's define the notion of convergent of sequence subsequence. Okay, so convergent of subsequence. Okay, now before I get into the definition, I would be making use of this term for the subsequence. I would write it down in this way: x n k. Okay, where this n1, n2, n3, nk, and this goes on is coming from the set S for which the restriction is made. So it is understood from there itself what is that set S. Okay, and the arrangement of the terms is done in this way so that you have nk greater than or equal to k. So let xn be a given sequence and xnk be some subsequence, be a subsequence, then we say, now you can see that actually ni's is varying. So instead of varying that each of this n1, n2, nk, you just vary this k. Just vary this k, and once you vary that k, everything will get very easily varied. Okay, so then we say that xnk converges to say some point x in R if for given, again the same definition, but you need to know what is varying. So for given epsilon positive, there exists, okay, now k is varying, so instead of n I'll be using the notation k. There exists a natural number, say k naught, such that such that the difference mod of xnk minus x is less than epsilon for all k greater than or equal to k naught. So definitely, if this k varies after certain time, then the suffix of x here in this xnk also varies. Okay, so this is the definition of a subsequence. We say that xnk converges to a point x if for given any epsilon positive, I'm able to find a natural number such that the difference xnk minus x can be made lesser than epsilon for all k after certain stage, that is for all k greater than or equal to this k naught. Okay, so the obvious question to ask is that if the given sequence is convergent, if the given sequence is convergent, then is the subsequence generated, any subsequence generated from this given sequence, is it convergent? And if it is convergent, where do it converges to? Okay, so the answer, I'm answering this question through this theorem with the justification. Let me call this as theorem. I don't know the number, so I'll skip that part. If xn converges to x, by the way, I'm talking about a real sequence, and if xnk is any arbitrary subsequence, then xnk also converges to the same limit as k. By the way, see, when I say xn converges to x, n is varying. So as n tends to infinity. So this is limit of the sequence xn as n tends to infinity. Through this definition, actually we allow only k to vary. So we don't say that as nk approaches to infinity. Instead, we just say that this k approaches to infinity, xnk also converges to x. Okay. Okay, so let's prove this. Just understand the definition of convergent of a subsequence using the fact that xn converges to x, and the definition of xn converging to x. We show that the subsequence, any subsequence, also converges to x. Okay, so that's answer my question. So what we say that any subsequence also converges to is convergent. Not only that, but it also get converges to the same limit. So to show that this section K is converging to X, we need to start with an epsilon positive. Just check the definition, and I should be able to show that there exists, say, some K naught in n such that this difference xnk minus x is less than epsilon for all k greater than or equal to k naught. And in fact, this idea flows very easily from the fact that nk is always greater than or equal to k. So if k is varying, then definitely nk also have to be. If k is greater than or equal to, say, at certain point, then obviously nk also have to be greater than. Okay, by the way, this xnk are the term from xn itself. So xn is like x1, x2, x3. So removing some terms from this x1, removing, say, some arbitrary terms from this x1, x2, x3, we form this subsequence xnk. Okay, so let's use the definition of xn being converging to x. So since xn converges to x, we are able to find a natural number, say n, such that the difference xn minus x can be made less than epsilon for all. Okay, I'll use the notation k instead of n for all. So mod of xk minus x instead of n, small n, which is varying, because here the k is varying. So instead of n, everywhere I'll make use of a small k. So for all k greater than or equal to n. Okay. So thus for k greater than or equal to n, what happens is that nk, which is also a natural number, is also greater than or equal to k, and that is also greater than or equal to n. So ultimately you have nk is greater than or equal to n, and therefore this result, this property which I have stated, the definition should hold for xnk also, because that is also the term of the sequence. Okay, so thus you need to have, hence whenever k is greater than or equal to nk, we have from star the difference xnk minus x is less than epsilon. Okay, so that's exactly the definition of sorry, k greater than or equal to n. By the way, I'm so sorry, here there's a mistake. So by the definition, we should be able to produce a natural number of n such that whenever k is greater than or equal to that natural number, xnk minus x, the modulus of xnk minus x is less than epsilon. So we have that. We have the natural number n. So the same natural number works. So whenever that k is greater than or equal to the natural number, mod of xnk minus x is less than epsilon. So this proves that thus xnk is convergent and converges to the same limit x. Before I end up this session, I have a question for you, for which on which you can think. Is the converse of this result is true? That is, if you can find a subsequence which converges to say some point x, thus the sequence is also convergent. Okay, we will talk on some more interesting result on the subsequences in the upcoming lectures. So stay tuned for the next lectures and continue studying analysis. Enjoy analysis. Thank you and have a nice day.